If you are serious about machine learning, you have to know what a transformer is, how it works, and what it enables you to do. In this video, we're going over the high-level concepts and dive into some of the algebra involved. While you will probably never have to implement a transformer yourself, it will still help you a lot to understand the inner workings of transformer modules. So without further ado, let's get to it. I want to split up this video is that I'm going to spend quite a bit of time on going over concepts in the beginning. So I have some visualizations about how the tensor math exactly works in transformers, in attention and transformer layers. And then in part two, I'm going to walk you through the code so you can also see how it's implemented. So I think if you pay attention to all of these all together, this will be very helpful to see the concept and then the code. So in particular, what I want to look into is transformer encoders, transformer encoder layers, and multi-head attention. So these are actually implemented modules in Torch, so you can actually readily use them. You don't actually have to implement them yourselves, but it still helps to see how they're actually implemented under the hood. So I'm going to look at these three and demystify them for you. Well, starting with the transformer encoder. So how to think about that as a high-level concept, right? If we really look at it very abstract, not knowing what's really going on in it, it is something that takes a sequence of inputs, and we're going to call them tokens, and the number of tokens that we have, let's say in the code we're going to be using, we call that end sequence. And each of these tokens are some kind of embedding, right? So these tokens will be an array of numbers. So if those were like word tokens, then we just use our normal word embeddings, and we'll have now n number of features for each of these tokens. Now we have n sequences and n tokens, and so that means this becomes a tensor of exactly these dimensions, n sequence and n features. And what the transformer encoder does on the high level is it gives you exactly that same dimensional tensor output. But now actually these embeddings know of each other. So these are new featureizations of the same sequence, but with the added benefit that now there is an interconnectedness, right? So now the tokens know of each other. So they have attention on the sequence itself. And so that makes them more valuable, right? That makes them more valuable for all the models we know they're being used in. So on a high level, what you can remember if you don't know anything else about transformers is that if you have a sequence of embeddings, a transformer encoding will make you a somewhat enriched sequence of the same embeddings. And the enrichment comes from a mechanism called self-attention that makes these embeddings know of one another in that sequence. Now in this, we're going to add a third dimension, and we'll get to that in the code too. So usually when you train or when you infer, you don't just use one sequence of tokens, you use an entire batch. And so we're going to have a three-dimensional tensor here, which is n batch times n sequence times n features. And if you run that through a Torch transformer encoder, you will also get exactly the same dimensional output. Now that is a transformer encoder. What is a transformer encoder layer? And that is actually very simple to break down. So transformer encoder is made up of multiple layers. So when you initialize a transformer encoder in PyTorch, you specify what is your layer and how many do you have, right? In this case, it would be 5 layers of transformer encoder. And what happens with our inputs as we pass them through, they will be sequentially passed through these transformer encoder layers. So obviously, if you have more layers, your encoder is more complex. If you have fewer, you have fewer complexity. So this is one way of just adding complexity to your encoder model. And now let's look into these transformer encoder layers in details. Really, what makes them tick and behave the way they do. So if we input our data set, again, this is n batch times n sequence times n features into a transformer encoder layer. they'll be passed into a multi-head attention module. So that's the key. We're going to get to that in the next part. Then what comes out is simply added to the input again, followed by a layer normalization, and then followed by a very classic feed-forward neural network, right? And that is a certain dimensionality, but it's going to be passed through this, again, added to the input, and then normalized. And optionally, you also have things like dropout for regularization in this, but this is how a transformer encoder layer works, right? And all these concepts like normalization, the feed-forward neural network, these are all known concepts. The multi-head attention is something we're going to dive in deeper a little bit. So multi-head attention, that's also implemented in PyTorch. So you don't really have to implement it, but it helps to know what's going on under the hood. And so we're showing this here as a concept, but also later in the code. So let's look at it. So multi-head attention. Attention in general takes a key, query, and value input, right? And this can be, again, a sequence of tokens of certain embedding with dimensionality and features. And the special case of self-attention is where all these inputs are simply the same input. So when we're going in the code later on, we're going to look into just the very special case of self-attention, right? The other case is cross-attention, where you have basically different types of inputs coming together, and that kind of works your embeddings all together. But in self-attention, these are all the same. But nevertheless, what's happening mathematically is that we're going to take the query input, we're going to transpose the key. Again, if we do a matrix multiplication of that, then we have this matrix of n sequence times n sequence, right? The dimensionality of the original embeddings is now completely taken out of that, and that's a kind of like an attention weight matrix across the sequence. Now, what happens further mathematically is that now you'll take a softmax of this. Again, this is after some normalization again, but you're taking a softmax of this. This doesn't change the dimensionality. You do a matrix multiplication with the value input. And what comes out is, again, the same dimensionality and features and end sequence. And that's what you call an attention matrix, right? So this is a self-attention matrix. There's a few more other things. There's some weight neural networks in there. We'll get to that when we get to the code. But that is essentially what happens. That's the key that makes your sequence embedding aware of one another. And now when we talk about something like multi-head attention, the difference here is we'll do exactly the same math, but before we do it, we break down the number of features into smaller tensors of dimensionality dim head, right? In this example here, we have 3 attention heads, and so our dimensionality of each head is the number of features divided by the number of heads. And obviously, this has to be mathematically possible, right? So your number of features have to be a multiple of the number of heads you want to use. And once you've broken down this, you do everything that I just showed within each head, create the attention metrics for each head, and afterwards you concatenate everything back again. We're going to do that in the code, and I'm going to show that. Okay, and so now we're going to dive into the code. And that's all happening in a Jupyter notebook. I have the code on my GitHub. The link will be in the description, so you can kind of get it and also follow along. But here it is what we're going to do. We're going to import just some of the libraries, so math, because we're going to need that just to make a square root, but also here our torch implementations, right? In particular, we're going to look at transformer encoder layer, and multi-head attention. So I'm going to import all of these. And then in the next cell here, I'm just going to give some random, well, quasi-random dimensions, right? So let's say batch size of 16. We have a sequence of n sequence of 20 tokens, right? Each of them, let's say, was an embedding of 512 dimensions. And then for the multi-head attention later on, we're going to take 4 heads. So again, this has to be divisible. The number of features has to be divisible by the number of heads. And then the multi-head attention, the transformer encoder layer, as you've seen, it has a neural network with a certain dimensionality. So that's in here. And then dropout, we're just going to have it 0 for now, but this could be any number between 0 and 1. So I'm just going to put that into our memory. And now we are creating just a random input, right? So this would be X of dimensionality and batch and sequence and features. And now we're going to make a transformer encoder layer. So this is the module that we can just take directly from PyTorch. We're going to look at how we would implement it later on too. But this is from PyTorch. It has certain inputs. There's more inputs with default values, but here's what I'm going to do. Dimensional of the model is the dimensionality of the input features, the input embeddings. The number of heads, that's the number of heads we want to use for our multi-head attention. So the more heads, the more complex you can think of your attention mechanism is. The dimensionality of your feed-forward neural network, dropout if you want. And then this flag here is just kind of handling the arrangement of the input. So batch first is really how I like it. If this is false, then it's I think it's first sequence, then batch, but I like it always like batch first, then sequence, then the embedding. And so if I create such transformer encoder layer, and I'm just going to pass it through, then what happens, these are all still untrained, but they have trainable parameters. So they pass through this, and the dimensional is exactly the same, right? And now, as we said, if we put multiple of these transformer layers together, then we have the transformer encoder in PyTorch. So what that takes in is exactly that, a transformer encoder layer and the number of these layers. And then they go one after the other and so on and so forth. And that also doesn't change anything on the dimensionality of the output. So again, what comes out is the same dimensionality as the input, but it's more enriched embeddings due to the self-attention that is being put to that. And so if we count the number of trainable parameters of an encoder layer and an encoder, we'd expect that we basically get the number of parameters just multiplied by the number of layers, right? So if I run all that, then exactly that's what we get here. This is the number of parameters in one transformer encoder layer. You see here, this is 2 million, and then since we had 5 layers, this is 5 times these this number of parameters, right? This is just a assertion here, checking that is really true. Now, if I wanted to make my own transformer encoder layer based on what I know about transformer encoder layers, then that can happen here, right? So I'm going to use the same inputs as the PyTorch implementation would take in. So we've seen it, the dimensionality of the model, number of heads, feed forward dimension, dropout, and then batch first, right? And I will put and use the PyTorch multi-head attention. Now we're also going to implement that later on, but here we're going to use the one that comes off the shelf in PyTorch. So we have a multi-head attention module here, and then afterwards we have a feed-forward neural network, and that is a linear layer that basically expands the model dimension to the feed-forward dimension, followed by a rectified linear unit and dropout if you want to, and then again linear that makes it back to the model dimension, right? So that X complexity. And layer norms play a role too. So how it all comes together is here exactly. So we're cloning X. So this doesn't have to be done explicitly, but here for overview, I do exactly that, right? So we're cloning X. We're putting X through this attention layer. So self-attention, key, query, value are all X. I apply a dropout. I add the original input to what comes out of the attention, and then I apply a layer norm. And then I clone it again. I pass it through the modules in the feed forward neural network. Again, linear, ReLU, dropout, linear. I'll apply another dropout. I add it to the original input, and I apply a layer norm, and that comes out. All right. And so if I run this, I have not yet defined it. I have to run this first. Oops. If I run this, then again, I get exactly the same output dimensions as before. And if I just kind of do a count of trainable parameters of my implementation versus the off-the-shelf PyTorch implementation, I have the same number of parameters, right? So now the off-the-shelf PyTorch implementation is not exactly the same. This is really just me writing out the code to give you the conceptual overview. But this is really what's happening, and this is something, you know, I could use now and to train. And now that we've done all that, and as you've seen, we've used this multi-head attention module. This is directly off the shelf from PyTorch. Now I want to make my own multi-head attention. So here we have, you know, the off-the-shelf multi-head attention. I want to have my own multi-head attention. I'm calling it unmask because there's also another concept called masking of inputs. I'll get that in another video, but here we're going to do unmask inputs. All right, and so I'm setting it up in the way I would, you know, with the same inputs that you'd have in the multi-head attention from PyTorch, the embedding dimensions and the number of heads. And then what makes it up is essentially 3 linear layers, each of the dimensionality of the model dimension for the query, key, and value vectors. And in the end, there is a linear output layer, also of embedding dimensions. And then in between, we're going to have the matrix multiplication that I showed. And so here in comments, I always kind of keep track of what the dimensions look like. So you also have that in the code, because it gets quite tricky, a couple of steps all at one time. And so it's really nice to keep track of what the dimensionalities are after each of these steps. So as I mentioned, if we put in a query, key, and a value vector, then what happens is we put each of these through the individual linear neural network and do then a little bit of reshaping here. And what that is basically dividing up the 3 dimensions now into 4 dimensions, where we add the number of heads in there. So now for each kind of batch item, and for each head, we have a number of sequence and the remaining dimensionality of each head, right? And we do that for key and value vector. So we have all these dimensions. And then in order to do the matrix multiplication, I'll do a transpose of that key vector, right? And I transpose basically the last 2 dimensions here with each other, so I can do the matrix multiplication with the query tensor, right? So this is a matrix multiplication. I go then through a normalization by dividing it by the square root of the head dimension. And what comes out is exactly what I showed in the presentation, right? We have n batch, n heads, and then n sequence times n sequence. So the dimensionality of the model is not in here anymore in those attention scores. And now I do the softmax as I showed. This gives me attention weights, and then I multiply them with the value vector, right? And when I do that, then what gets out is again this n batch, n heads, n sequence, head dimensionality. What I have to do now is just put the heads back together, right? I reconcatenate them, and that's what I do here, right? So I do a retransposing, I'm doing a reshaping that will basically bring it into that form, and what comes out is n batch, n sequence, n features, followed by one more linear layer output, and then I can return it, right? So one is the matrix of the attention output, and that has these dimensions, and then the attention weights is essentially that matrix of and sequence times and sequence. So I'm going to do all that, and I can run that. And I'm also just going to look at the trainable parameters. They are the same for these two implementations. And I also want to just look at the first item of attention is the self-attention output. And I'm just going to look at that for my implementation and the PyTorch implementation. And as I'm expecting, it has, again, the same sequence, end batch, end sequence, and the end features. So the code is on my GitHub. Feel free to check it out. Feel free to ask me questions. This is a field that can be broad or deep. If you want to know something in more detail, please let me know, and I'll work on it. I want to make it as clear as possible for everyone who watches my videos. Thank you so much for making it all the way to the end, and hope to see you in the next video.